So this lesson's topic is continuity. So when is a function continuous? Well, a function is continuous when you can draw the graph without having to pick up your pencil or pen. That's a very non-mathematical definition, but it works. Right, so say this graph is continuous, right? But this is not, because we have to jump here. This is not, because there's a hole there. There's a hole at this point. So the function is not continuous at this point either. Why? Because we have to stop, pick up our pencil, and continue. And then graphs that have vertical asymptotes are not continuous either, because there's a big break there. Okay, so in more mathematical formality, let's define the three conditions that are necessary for a function to be continuous at a point. So three conditions for a function to be continuous. Okay. At the point x equals c. Right, so the first condition is that the function has to exist at that point. Okay, so f of c has to exist. The second condition is that the limit of f of x as x approaches c, that too also has to exist. And the third condition is that f of c, the function, has to equal whatever the limit is equal to. So these three conditions have to be satisfied for the function to be continuous. Okay. First, the function has to exist at that point. Second, the limit has to exist at that point. Third, the function, whatever the function is equal to, has to equal to whatever the limit is equal to. Okay, so let's explore the four types of discontinuities. Okay, so the first one is called a jump discontinuity, right, because we see that there's a jump in the graph, there's a break in the graph there. So jump discontinuity, and why does this fail? The continuity test. Well, because does f of c exist? Let me do this. Let me show this here. Right. So, there we go. So does f of c exist? Yes, it does, right? Because it exists right there. So the second question is, does the limit exist? And the answer to that is no. Because for a limit to exist, the left-hand limit must equal the right-hand limit. And in this case, that condition is not satisfied. So that's why the function is discontinuous at x equals c. Okay, so a second discontinuity is called a point discontinuity. Sorry. Let me get new sheet paper. So, like that. And this is called a point discontinuity. And what happens here is that the function follows this line everywhere except at this point where it sort of jumps up. So this is called a point discontinuity. So let's do the test again. Does f of c exist? Okay, so say c is at this point. Yes, it does, right? Because it is defined at this point here. Okay, so yes. Second condition, does the limit exist? Well, yes, it does, right? So because it goes together at the point. Remember that with limits, we don't care what happens at x equals c. We just care about what happens around x equals c. So yes. Third condition, okay, does the limit equal the function? No, right? This is not equal to this thing here. So that's why it fails. So the limit does not equal the function. Alright, the third type of discontinuity is called a removable discontinuity. And that occurs graphically. It's going to look like this. Okay. So this is called a removable discontinuity. So in this case, this is a bit tricky here. Removable discontinuities are going to occur in rational expressions when both the numerator and the denominator both have a common factor which you can cancel out. What? Okay, so graphically it's going to look like this. It's similar to a point discontinuity, but look here. The function is completely undefined at this point. So the reason why this point is, why this thing fails, is because S of C is undefined. Okay, we'll come back to this later. Now I'm just do the last discontinuity quickly. It's a simple one. Right, so and the last discontinuity is called an essential discontinuity. Okay, see that? Okay, good. It's called an essential discontinuity because it's an asymptote. So essential discontinuities are going to occur with vertical asymptotes. Okay, they're going to occur with vertical asymptotes, and you can see that there's a huge break there. So that's why we have a essential discontinuity. Okay, now back to this removable discontinuity, third type. So this is the second type. This is the third type, and this is the fourth type. So with removable discontinuities, I said that they have to be rational functions. And essentially, sorry, not this essentially, but with removable discontinuities, you can sort of remove the discontinuity if you sort of redefine the function. Confusing? It's just because I'm explaining it kind of poorly. So, let me give an example to help not confuse you. Okay, so say I have this function here. Okay, so f of x is equal to x squared plus x minus 2 all over x plus 2. Okay, so let's try to figure out the special characteristics of this graph. Well, x plus 2, so we see that there's a vertical asymptote, so let's set the bottom equal to 0. Therefore, we have a vertical asymptote at x equals -2. Hold on there. Is that right? No. Right? Because remember with vertical asymptotes, the bottom has to equal 0, but the top cannot equal 0. If we plug in -2 here, we see that 4 minus 2 minus 2 equals 0, so 0 over 0. So, nope, it's not a vertical asymptote. So what is it? Well, let's factor it, and let's take a look. So this factors out to what? X plus 2 times x minus 1. And notice that we have a common factor to both the top and the bottom. So the definition of a removable discontinuity is a rational expression, okay, where the top and the bottom, where the numerator and the denominator both contain a common factor which can be cancelled out. So once you cancel it out, we get this thing here. So in a sense, we sort of removed discontinuity by cancelling out like terms. Now one thing here, if we redefine this, we have to keep in mind that this new function is not defined at x equals -2. Right? So in order for these two things to be equal to each other. Okay, so this function here and this function here, they're the same at all but one point. And the point at which they're not the same is x equals -2. So let's graph this. So we can actually use this thing to graph it here because they're the same thing, except at this point. That's why it makes sense, right? X cannot equal -2 for this graph. So, so it's going to look something like this. Okay, so you can see that we have a hole. Right? We have a hole here at -2, -3. Right? Because this function is not defined at this point. So this is, in a sense, removable, in that if we redefine this function as simply x minus 1, then this hole disappears. Okay, so this is called a removable discontinuity. And all the other kinds of discontinuities are non-removable. Okay, so this one's non-removable, nor is a point discontinuity, nor is an essential discontinuity. So the other three types of discontinuities are non-removable. Only this type is removable. Wow, I'm having trouble speaking today. Right, so just a simple definition here. So if a function is continuous at each point in the open interval a, b, then the function is said to be continuous on the open interval. So this is AB. So this is just defining what we mean by continuous. Okay, so we can say a function is continuous from -1 to 3. That means that there's no breaks in it. And so what happens if the function is continuous on an entire graph? So if the function is continuous at each point in -infinity to infinity, then the function is said to be everywhere continuous. So if it's continuous from -infinity to infinity, then it's said to be everywhere. And the function is said to be everywhere continuous. Right? Okay, so that's that. Now, just for some quick examples. Okay, this lesson might go over. I'm sorry, but so we have a split function here. So x plus 2 if x is greater than 1, and x squared minus 1 if x is smaller than 1. And okay, so say the question was find where the graph is discontinuous. Okay, so we say here that potentially there might be a jump at this gap here. So we're gonna take a look. So first question is f defined at x equals 1. Answer is yes, it is defined and it's equal to 0. Right? Second question. Does this limit exist? So does this thing exist? So to do that, we have to first see if the left-hand limit and the right-hand limit equal each other. So the first step is to find the left-hand limit. And you can simply use direct substitution here. Right? So you can use direct substitution. So coming from the left, 1 minus 1 equals 0. What about the right-hand limit? Coming this way equals 3. We see that the left-hand limit and the right-hand limit do not equal each other. Therefore, the function is discontinuous at x equals 1. Right, okay. So the function is discontinuous at x equals 1. Okay, so let me give you another example. So we have 3 more examples. So the function is going to be x plus 3 if x is greater than 3, and x squared minus 3 if x is smaller or equal to 3. So let's do this test again. F of 3 is equal to 9 minus 3 equals 6. So does this limit exist? So let's first do a left-hand limit. The left-hand limit is going to be simply a direct substitution. 9 minus 3 equals 6. The right-hand limit is going to be like coming in from the right. So 3 plus 3 equals 6. They equal each other. Congratulations. Okay, so the limit does exist. Third question. Okay, does the function equal limit? And yes, it does, because 6 is equal to 6. Okay. So let me give you an example of a point discontinuity. Okay, this is kind of a redundant example, but I'm starting to graph. You should get it here. Okay, we see here that at x equals 3, so the function is defined at x equals 5, and that's equal to 3. The limit is also existent, and it's equal to 9 minus 1 equals 8. However, the function does not equal the limit. So these two are not equal, and therefore the function is not continuous at x equals 3. So what we have is we have more or less we have a jump there. Right, so remember that any graph can have more than one discontinuity. So say I had this graph here. So x squared plus x minus 2 all over x squared plus 5x plus 6. Okay, so let's factor that out. So we see here that we have a removable discontinuity at x equals 2. So wait, so first of all, where is the function discontinuous? It's discontinuous at x equals -2 and x equals -3. So it's going to be discontinuous wherever the bottom is equal to 0. Okay. Second question, is it going to be a removable or a non-removable discontinuity? So we see here that we can cancel x plus 2 from both the top and the bottom. So therefore, we're going to have a hole at x equals 2. So the function has a removable discontinuity at x equals 2. But then what we have remaining here is this x minus 1 all over x plus 3. So that's going to be a vertical asymptote, right? Because it can equal 0 on the bottom. So if we plug in 3 here, we have 0 in the bottom, but not in the top. And the top is going to be, what, -4. Right, so we have a vertical asymptote at x equals 3, and we have a hole at x equals 2, -2. Okay, so in this case, we have a function that has two different types of discontinuities. Right, so that's that, and so let me wrap it up. Sorry, it's becoming long. So let me just make sure that you conceptually understand why this is so. Why we need to, why a function needs to fit these three conditions. So the first thing is that the function has to exist, right? So in order for us to first draw the graph, the point has to exist. Second of all, the limit has to exist. Now remember that with any limit, if the limit does exist, that means that the left-hand limit and the right-hand limit are going to be equal to each other. Can't find it. Okay, so say, okay. So, first of all, the point has to exist. Second of all, the left-hand limit and the right-hand limit have to equal each other. Right? So, if they equal each other, that means that that means that the function is going to be, like, around each other at x equals 3. Let me rephrase that. If the limit does exist, that means that there's not going to be a break. So, if the limit does exist, that means that this thing's not going to happen, right? We're not going to have a function coming this way here and this way here. Instead, if the limit does exist, that means that the function is going to be meeting each other around the point. And this last condition states that the point that does exist has to equal whatever the limit comes to. Okay? These are supposed to be our signs here. So it could be that the function is defined here, but the limit comes to here. And if that's the case, then the function is not continuous, right? Because it's not going. The limit isn't approaching where the function actually is. So this condition helps us ensure that, yes, where the limit goes is where the function actually is. And in this case, we can be sure that we won't have to pick up our pencil when we draw it, because it's continuous. Okay, that's my lesson on continuity. Long, 20 minutes. Sorry about that. Okay, see you next lesson.